Okay, number 3 on the homework. We have a function. We know that, actually, let me grab the directions real quick. The directions are to use the remainder theorem to determine if the following roots, if the following are roots to the given equation. If so, find the other roots, then write the function in factored form. If not, just say that it is not a root. So what its meaning is -3. Is -3 a root? You're going to determine that by plugging -3 into the x's. If you get 0, the answer is yes, it is a root. Okay, so I've rewritten the polynomial, but -3 is plugged in. You can go ahead and grab a calculator. -3 cubed, -27. 2 negatives multiplying makes a positive. And then if I'm multiplying by 3, let's see, that means 20 times 3 minus 3, 57. And then minus 30. When I look at these two, I see that I have -57 plus 57. This is 0. So that means -3 is a root. Now, if -3 is a root, that means that x minus -3 is a factor. I need to divide this polynomial by x plus 3 to begin factoring this third-degree polynomial. So I'm going to set up the boxes. And I'm dividing by x plus 3. I need the interior of the boxes to be this polynomial. I'm going to erase a little bit here so that you can see more clearly what it is we're looking at. So I've got x cubed is my leading term. That's going to be the first item in the upper left of the box interior. The next thing that I'm going to do is I'm going to begin my division. I can figure out what goes here because I know that this is x cubed. X times what is x cubed? And that's x squared. Now, at this point, I can do x squared times 3 and figure out what goes in this box. My next step is to realize that these pair of diagonal boxes are going to add together to make the x squared term of this polynomial. But where is x squared? If x squared isn't there, then that means I have 0 x squareds. So what do I need to add to 3x squared so that I have no x squareds?
-3x squared.
Thank you. That's it, -3x squared. Then I am ready at that point to figure out what goes here. I need to multiply to x to get -3x squared. I will multiply by -3x to give me that -3x squared. Now I can find this box, 3 times -3x. And here we go again. When I add these two diagonal boxes together, they are creating the x term of the function I'm trying to divide. I need to make that a negative 19x. So what do I need to add to negative 9x to get negative 19x? And hopefully you see it's negative 10x. Then I'm ready to figure out what this next piece is. I am going to look at x times what is negative 10x. And be aware that as soon as you write in one of those spots just a number, you cannot go any further over here with your quotient. That means anything, the entire polynomial either needs to be to the left of this line or you've got a remainder, is what that is basically saying. And if we found that plugging in negative 3 made this 0, then I should not be having a remainder. So now 3 times negative 10 is negative 30. That had better be what's over here, and it is. So all of those in the boxes added together make that polynomial. That means that x plus 3 multiplied by x squared minus 3x minus 10 is the beginning of factoring this polynomial. Now, x plus 3 is a nice linear factor, but what I have here is quadratic, and I can factor that into two linear factors. Since I have an understood 1 multiplied to my x squared, that makes this a little bit easier. I'm only looking for two numbers that multiply to make negative 10. And add to make negative 3. And that's going to be negative 5 and positive 2. And now I have factored this into all of the linear factors. I'm ready to now say what the remaining zeros are. I already knew the 0, negative 3. And now I can find the other two by looking at what makes x minus 5 equal 0 and what makes x plus 2 equal 0. And that would be positive 5 and negative 2. And so those are my remaining zeros. And then, yes, I can explain the minimum degree problems. And also, when class was over, I kept recording and I talked through how to do it. I don't know if you watched the video. So I think what I might do is start by looking at the classwork and make sure that you understand that. So the issue is, first of all, how many minimums and maximums do you have? When I look at number 3, I see one minimum, but I don't see anything else that's a high point or a low point. But you also want to be on the lookout for what I described as wiggles. And I consider a wiggle to be something where you should see an inflection point, where it changes from a happy face to a sad face or vice versa. But what you can imagine that's happening is there's a tug on those 2 points where the graph was trying to create a relative minimum if it was able to go a little farther with that pinching stretch, and it was going to be creating a relative maximum. It was trying to do that, but didn't quite make it. To get that wiggle going, there has to be a higher degree polynomial involved to even begin creating that stretch that is attempting to create a relative minimum and a relative maximum. So when you see something that wiggles like that, you want to recognize that as worth one minimum and one maximum. If you count the number of minimums and maximums with the understanding that the wiggle thing is counting as 2, I have 3 in this situation. The minimum degree of my polynomial is always 1 higher. So that means this is a minimum of degree 4. And I want you to also notice that you should expect that because the ends are both going up, they're in the same direction, that your degree has to be even. It has to be an even degree. That can be an extra check that you do to make sure that you're doing this right. And I just want to double check, is everyone paying attention? Or you know it already, one or the other? Okay. So keep in mind that even odd issue. Because the right end goes up, you know that the leading coefficient is positive. Number 4 is easier to spot. 1 relative maximum, 1 relative minimum, another relative maximum. That's 3. Add 1 to that, 4. The leading coefficient is negative on this one because the right end heads down. For this problem, you have a relative maximum, a relative minimum, and then you look at this and you go, I don't have a minimum maximum in this little wiggle here, but that requires a higher degree polynomial to be working on trying to stretch those a little farther. It's attempting a minimum maximum, but it's just not able to complete it. So that's going to count as 2, 1 maximum, 1 minimum. And then I have another pair of maximum minimums. So that is looking at 6 maximum minimums, add 1, 7. The minimum degree is 7. It could be degree 9, it could be degree 11. And the leading coefficient is positive because the right end goes up. But do notice that you expect this to be an odd number because the 2 ends are going in opposite directions. So now I'm going to a little bit more quickly do these. Relative maximum, a wiggle attempting to stretch into a pair. So that counts as 2, 1, 2, and then 3. Add 1 more. This is minimum degree 4. For this one, you have a relative minimum, relative maximum, relative minimum, relative maximum. And I want to point out that if you're looking at the graph through here, do you see that it's ninja slicing through? And I'm sorry, but when I say ninja slice, I'm referring to that silly game where you slice the fruit. Yeah, Fruit Ninja. So if it's slicing through like a Fruit Ninja, that's not a wiggle situation. So it's not creating any extra degrees that you have to have. And all you have are 4 minimums and maximums. Add 1, that's 5. 5 works with this because that means odd degree, and these are going in opposite directions. So this is either degree 5, 7, 9, or so on. The leading coefficient is negative because the right end heads down. And then this one you should notice you've got a minimum, a maximum, a minimum, and then you want to notice that this is doing ninja slicing, but this is not. You should see that the graph kind of wiggles a bit. That is requiring 2 more degrees of a polynomial where it's trying to stretch to make another pair of minimum maximums but failed. So 1, 2, 3, and then this counts as 4, 5, add 1, 6. The minimum degree is 6. And notice that both ends are going in the same direction. It should be even. And the leading coefficient is positive because the right end heads upward. So that's what you need to be looking at with those. And now I'm going to take a look at the homework problems. And if you weren't sure how to do them, hopefully you do now. And so look at it with me. You should see 1, 2, 3, 4. That's either a wiggle or it makes a minimum maximum. However you see it, it counts as 2. So that means 1, 2, 3, 4, add 1, 5. Take notice that the ends go in opposite directions. It should be an odd degree. And you have a minimum odd degree of 5. The right end heads down, negative leading coefficient. This one, you should see 1, 2, 3. Add 1, 4. Heading down on the right end. And then over here, this one is a tougher one. I've got 1. Now, when I look at this piece right there, it might be having a little tiny relative minimum, relative maximum, or it's a wiggle. Either way, that counts as 2. So I'm up to 3 now. Then I notice this low point, add 1, that counts as 4. And then this little wiggly possible minimum maximum pair comes again. Whether it's a wiggle or an actual minimum maximum, it's worth 2. That takes me up to 6. And after you do your count, add 1, 7. This is minimum degree 7 with a positive leading coefficient because the right end goes up. And I want to say again, the ends are in opposite directions. You are expecting this to be an odd number, and it is. Okay, so hopefully that helps you out. Why do we add 1? Let me say this. If I'm looking at a degree 1 polynomial, I'm dealing with something that either has a positive slope or a negative slope, and it's a line. It doesn't have any relative minimums or maximums. You know, before you came into this class, you knew that, and you also knew that with degree 2, you got parabolas. Parabolas have only one turning point. They have one relative minimum or they have one relative maximum. So it's really about the pattern. If you look at a degree 3 might just wiggle, like x cubed just does a wiggle, but it might also actually turn 2 times. But if you have a degree 3, this is the most you can cause to happen. Now, you're getting to see, to do graphing based on factoring linear factors. If I have degree 1, then I'm only dealing with one linear factor. I'm going to make one up. Let's say it's x plus 3. If I have a degree 2, I have two linear factors. Maybe it's x plus 3 and x minus 1. Again, I'm just making it up. If I have degree 3, I have three linear factors. Maybe it's x plus 3, x minus 1, and x plus, I don't know, 5. And basically, as you bring in another linear factor, it allows it to go through yet another bend. Each of those is helping. Does that actually help to kind of think about it that way, that as you add an additional linear factor, it allows it to change direction one more time? And it may help if you look at, when we look at our multiplicities, when a 0 has a multiplicity 1, it slices through the x-axis. Multiplicity 2, it bounces. Multiplicity 3, it wigglies. And then 4 is just going to be another bounce, but it's a much steeper bounce, but you don't have to worry about that. And you can see that you get a turning point when you have two linear factors. With three linear factors, you get a wiggly thing. And perhaps that will help you to see why it is that we're adding one. It's more an issue of the pattern that we're getting as to why we add one to the number of minimums, maximums. And then again, that wiggle, that inflection point that doesn't quite create a relative maximum minimum, counts as one relative maximum and one relative minimum. Okay, then what other problems do you need to see from yesterday's homework? And if you're out here, you can hold up fingers. Anything else? I'm giving you a chance because some people are slow at going, oh, she's asking for a question. What was my question? Because I understand I can be that way too. Our minds wander at varying degrees. Some people have greater struggles than others, so I'm going to keep going. Hey, at least I need to try to remember to do that. Okay, are we ready then? Okay, we are moving on to a last classwork. The last classwork of dealing with polynomials. And I want to remind you that I'm going to do a little bit of statistics just to clean up before we go to spring break. And that way you come back from spring break and we can restart. And we're going to start with rational functions, which are looking at a polynomial divided by a polynomial. So what we're doing here is key preparation for that. You need to know how to deal with polynomial division. But on top of that, you have to understand polynomials well for this next unit to go smoother, the next one that's coming. So here we go. I'm going to look at what I'm dividing by, and I'm just going to make that a column over here on the left, 3x squared minus x minus 3. And then I want to realize that this polynomial being divided is what's got to show up inside these boxes. The answer to the division is going to be what we end up getting up here. So we're going to start like we started before with take the leading term, put it in the upper left box. The next term we're going to need to create is 13x squared. But I want to tell you ahead of time that we're going to get 13x squared when we add these two boxes together. And I want to definitely pre-warn you that the next set of diagonals under that, there are 3 of them, and that's what's very new. Those 3 are going to need to add together to make negative 11x. And then we still have our constant to deal with, but I'm going to start by just letting you know about that. Here we go. You need to figure out what goes here. So 3x squared times 2x, yes? Then fill in the rest of the column because you have that 2x. 2x times negative x, 2x times negative 3. And once you finish a column, it's very important that you understand what must come next. You must next figure out what that is, because only those 2 boxes can add together to make 13x squared. I have to make sure that that box allows me to add to negative 2x squared and get 13 of those. So what do I add to negative 2x squared to make it 13x squared? Da, 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 da. And then you can go like this. Okay, so 15x squared. All right, so that's done. With that placed, you now have no choice for what goes here. What goes here has to multiply by 3x squared to get 15x squared. And that's just going to be 5. And I want to remind you that the second you put down a constant, that's the cutoff for the full polynomial. If I'm not able to put this entire polynomial into those 6 boxes, everything else is going to be a remainder. So let's see what happens. Once I know that this is a 5, I can now determine what these 2 absolutely must be. So 5 times negative x, 5 times negative 3. And so does that make a complete polynomial that this is? No. Frustrating, frustrating. I did get the negative 15, but I did not get that negative 11x. Erg. So I need to, or did I? Or did I? So I need to look at these 3 add together to make negative 11x. Do they already add together to make negative 11x? Oh my goodness, they do. I don't need to add anything more on. And then, does negative 15 take care of the entire constant? Oh my goodness, yes it does. We don't have a remainder. What? That doesn't always just magically happen. Now, what I want you to do is recognize the quotient. The quotient is the result of the division without the remainder, if there was one. The remainder is 0. And then I want you to look at the 2 different ways you could possibly be asked to rewrite. Either you're rewriting the polynomial that you began with, and the polynomial we begin with is 6x cubed plus 13x squared minus 11x minus 15. Either we take the division and use it to rewrite the polynomial, or we write the answer to the division, which is what the second part is saying. So with the second part, this is expressing, actually, let me do this. I'm going to use blue and say, the one we just looked at, p of x written in blue, the polynomial we began with. And to overcome the color blind, I'll use red. This is looking at what is the answer to the division. So that means the polynomial we began with, 6x cubed plus 13x squared minus 11x minus 15, divided by that 3x squared minus x minus 3. What is that equal to? If you're rewriting the original polynomial, then you're going to take the divisor, 3x squared minus x minus 3, and multiply that divisor by the quotient, and then add the remainder. But I have 0 remainder. What that means is, if you have that 0 remainder, that means you just factored a little bit. Division is factoring. Every time you have factored, you've actually been looking at a way to divide. So you don't need to write the plus 0. And then for the result of the division, you're just going to put down the quotient, 2x plus 5. And then if there were a remainder, you would put that remainder over the divisor, which is the lovely 3x squared minus x minus 3. But since the remainder is 0, there's no need to write that because it's just 0. So I'm going to erase it. You don't have to write it. You can if you want. But I want you to see that the result of the division is 2x plus 5. That is one way that I can use the division that was done. The other way is I can use it to rewrite a polynomial in a factored form. And both of those can be useful. All right. You are now ready to start example 2. Yay! Isn't that what you're saying? Are you saying yay? I wanted another polynomial to divide. Oh my goodness, can't get enough of it. Oh, did I make a mistake on the answer key? Let's see. Are you talking about number 1 or a later number?
Yeah, I'm talking about number 1. I was just confused because it said the result of the division.
Uh-huh.
But I 2x plus 5.
This right here. With the result of the division, I didn't write here the plus 0 over the divisor. And admittedly, I wrote the plus 0 here. Plus 0 doesn't have to be written. So does that make sense?
Yeah, I understand.
Okay.
You were supposed to divide by 3x squared minus x.
Oh my gosh, I see exactly what you're saying now. I see where I'm wrong. I wrote this weird, and I need to fix that. So that will be one of my fixes today. This is supposed to, thank you for pointing that out. That took me a while to even see. Okay. Yeah, it's supposed to be that divided by that. That didn't make sense, did it? Ha ha ha. I am going to grab that so that I don't forget that I need to fix it. Where am I going? Do, 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 do. Do, do. Do, do. Okay. I greatly appreciate you pointing that out. Okay, perhaps you started this already, but I warn you, you really want those diagonals to line up. It makes a huge difference when you are doing polynomial division to account for every degree term that you have. I'm dividing by 3x squared plus 1. I've got a degree 2 term. I don't have a degree 1 term, so that's a 0x, and I have a constant. All need to be accounted for if I want this to go smoothly. If I account for each degree of the divisor, then I'm going to be working with, this will be just the leading term. The diagonal underneath that is going to be the next degree down. So I start with a degree 4 with my 18x to the 4th. This next diagonal must be x cubed. Those are going to need to add up to make a positive 9x cubed. The next diagonal underneath that is 3 boxes. Those 3 boxes are going to need to add together to make a positive 3x squared. But notice that that is not explaining another couple of terms. So I've got x to the 4th, x cubed, x squared. There's also an x term, but that's a 0x. There's also a constant term, that's 0. You have to make sure that you end up with a 0x and a 0 constant. Now, let's go through the work. I'm going to erase a little bit. Okay. 3x squared times 6x squared will give me 18x to the 4th. When I multiply that by 0x, I'm going to get 0. If you want, just throw 0 down. 6x squared times 1 will give me 6x squared. Now, it's very important right now that you realize that that 9x cubed is only going to be found by adding these two. That means that this one has to be that 9x cubed. Next, 3x squared needs to multiply to 3x to get me the 9x cubed. Once I have that, I am ready to finish this column. 3x times 0, 3x times 1. And now you're at a stage where you must find that last green box. These 3 are the only things that are going to add together to create 3x squared. So 6x squared plus nothing, and I need to then add a negative 3x squared, so that when I add all 3, I get 3x squared. Once you have determined what that box has to be, then you're ready for the next stage of 3x squared times what? Negative 1 is the negative 3x squared. I just wrote a constant down for my quotient. That means that either the entire polynomial occurs to the left of this line, or I have a remainder. So let's find out how it goes. Negative 1 times 0 is 0. Negative 1 times 1 is negative 1. Now, I only highlighted the yellow for x to the 4th, the blue for x cubed, and the green for x squared. I'm going to go to a highlight color pink to distinguish that my next diagonal underneath green are these three. I need to make 0x. When I add what I have so far, I have 3x. I have to add a negative 3x to make it go to the 0x that I'm expecting to get. And then there's another row. So new highlight color. This box plus this box. And I don't know, I guess I could say, hey, plus this box maybe, but you know, we've already gone over the line. Once we go over the line, there's nothing else I can bring up here to make things work out, to create what I'm trying to create. So I don't need to go up to this third box. It's just kind of a waste of time. Because once this line is drawn, it's just everything that isn't created before that line has to be added on to create that polynomial, and it's going to be part of the remainder. I've already got a negative 3x. I now need to make a plus 0, so that means I'm going to have to add 1 to the negative 1 so that I make it 0. Now I can write the answers. The quotient is 6x squared plus 3x minus 1. The remainder is negative 3x plus 1. And now we want to look at the two ways that we can rewrite the result that this gave us. Either we're going to rewrite the polynomial, and I need to be able to see it. Oh, 10 minutes left. I need to rewrite this polynomial. That polynomial is 18x to the fourth plus 9x cubed plus 3x squared. And that's called the dividend of my division. That polynomial is equal to the divisor, which is the 3x squared plus 1, multiplied by the quotient, which is 6x squared plus 3x minus 1. And I've got to have a parentheses around those two. And then plus the remainder. I'll put a parentheses, but I don't need to, just to overemphasize that that is our remainder. The other way that you might be expected to use this division is to come up with a result of the division. The result of the division is going to be, you were asked to divide 18x to the fourth plus 9x cubed plus 3x squared by 3x squared plus 1. The result of doing that division is the full quotient, 6x squared plus 3x minus 1, plus a remainder that you were not able to take through the division by the 3x squared plus 1. So just to make sure we're clear, you are getting a full polynomial and then a remainder. So that means that 3x squared plus 1 is not a factor of the 18x to the fourth plus 9x cubed plus 3x squared. But this at least tells you a way to rewrite that division. Because when we go into the next unit and we start looking at rational functions are going to look like this. And the division that is done here is going to tell you information. We're not there yet, but I just want you to know that that's why you need to know how to do this division. And I believe that is the rest of that classwork. That means we are done. What? And I can go over any additional questions you have, or you can get started on the homework. And I'm going to say again that I'm not giving quizzes at this exact moment because I am so severely behind with everything. Oh my goodness, I'm trying not to stress. Whew, okay, we're good. All right, so tell me what your needs are. Oh, why did you put negative 3x? I'm guessing that's going back to something. When was that? That was put down like 5 minutes ago. Let me see. Okay, I think I see where that question came from. Okay, so let me talk through what is here. You need the interior of the box to add up to just this. Before this red line, the boxes are adding up to 18x to the fourth plus 9x cubed plus 3x squared plus 3x minus 1. This is not the polynomial that we were dividing. So once you write down this constant for your quotient, draw a line, and if the interior of these boxes does not add up to the polynomial being divided, you have a remainder. To find that remainder, you have to look at what is excess. And so when we compare, we were making, let's see, what color can I use to not confuse? Oh, maybe an orange highlight, but that's kind of dark. And I know that's going to be troublesome. Ooh, light blue highlight. No, I already have that. Okay, whatever. This right here created 18x to the fourth. I had to come up with 9x cubed for this term. These three boxes were the only ones that were going to add up to make a 3x squared. That forced me to have to make this a negative 3x squared. But after that, I ended up with things that needed to have more brought in to get the correct term for x and to get the correct constant term. And I'm supposed to be getting 0 for those two. So as I look along the diagonal, I see I've got 3x, but I need to have 0x. So I have to add an extra negative 3x, but I'm not getting that from the left of that line. Anything to the right of that line is part of the remainder. And you're just not able to do its division with the 3x squared plus 1. And then this negative 1, I need my constant term to be 0. So I have to add 1 to it to make it 0. But whatever I have to add on after this line is the remainder. So did that make sense? I just want to know if that made sense, because if not, I can re-talk through it. I just need to know. Okay, good. All right, so polynomial division is actually not too bad. You just have to know how to organize it. And then it works out really nice. keep in mind the issue of putting placeholders for 0, because you need to account for, okay, I'll pink underline. The leading term, the highest degree that you see, the highest exponent is 4. That means that this polynomial has to account for exponent 4 on an x, exponent 3 on an x, exponent 2 on an x, exponent 1 on an x, and then a constant. What I'm dividing by, I also have to account for, but I'm looking at first, what is the largest exponent? That largest exponent is 2. So I have to account for x to the second power. I have to go down 1 and account for x to the 1 power, and I have to go down 1 and account for the constant. And that's why I wanted to create this extra row to account for 0x. This helps with keeping it organized so you don't get lost with 0 issues, because 0 issues show up and you have to know how to cope with them. The fact that I didn't have a 0x or a constant term for this polynomial I'm dividing didn't mean that I didn't need to look at that. That meant I still had to account for it, and I had to make sure to add to it to create 0 for both of those. And then if you set it up where your divisor accounts for every degree, and you put your leading term of what you're dividing there, from there it should just flow. And it'll line itself up as it needs to. And, well, there we are. Woo, lunchtime. I hope you enjoyed this class, and I'll see you later. Leave those nameplates because it lets me know where things have been sat in today. And I'll see you, I guess, next week. Bye-bye. Bye-bye. Bye-bye online. Bye-bye. Oh, there, I'm getting both cameras. Bye-bye. Anyone have questions?
I do, if that's okay.
Yeah?
I sent you an email. I was gone.
Actually, hold on one second. Hold on one second, because I just remembered I need to stop my video.